my introduction is going to be very brief because we've been having the candidates kind of introduce themselves and what they want to say about their background, which is great. So again, we're welcoming the final speaker in our series of the Future Leaders Program, Sebastian Fernández, who's currently at Stanford in electrical engineering, working on his Ph.D. He'll talk about his research today on perovskite optical devices, and also provide a little bit of background on kind of, where he's from, where he's going, and also one reason we're recording. So Sebastian, I'll let you take it away.
Great. Yeah, thank you so much, Lincoln. Yeah, so as Lincoln said, my name is Sebastian Fernández. I'm an electrical engineering Ph.D. candidate at Stanford University, and it's my pleasure and honor to talk about some of the work that I've been doing towards enabling emissive perovskites within the visible and ultraviolet spectrum. And yes, we will be recording this session just because I was a undergraduate TA at Georgia Tech, and I posted all my lectures on YouTube, and so I have like a decent following on my channel. And whenever I was an undergrad looking to, figure out what advisor or who I wanted to collaborate with and research, I always found it very helpful to see someone kind of give a seminar and understand how they think and what they work on. And so I just paying it forward and offering that opportunity to the next generation. So cool. Yeah, I think first I'll start off with a background on myself. See if this works. Okay. So, and let me move the viewer. Okay, great. I'll move this down here. Okay. I'm still looking at the screen, but please let me know if there's any technical difficulties.
No, looks good.
So, great. All right. So about me, I was born in Cusco, Peru, which is shown here, and actually lived 10 minutes from the Plaza de Armas, which is shown in this picture here. And then at the age of 2, I actually immigrated to the United States and find myself in Alpharetta, Georgia, where I spent a lot of my time playing the violin, which I spoke to Lincoln about briefly here, and actually had a really nice time one time when I went to Chicago for the Midwest Conference, and I was able to perform and be with some of the musicians from the Chicago Symphony. After that, graduating from high school, I made the very dramatic leap to Atlanta, Georgia for my undergraduate degree, where I was at Georgia Tech and studied electrical engineering. And most of my research was conducted within the silicon germanium devices and circuits team, led by Professor John Kressler. So I remember very vividly at the time that within my undergraduate degree, I found that nanotechnology and semiconductors was truly my passion for many reasons, but one of them being that we could solve very pressing societal problems with these very tiny devices. And so that really attracted me, and I looked towards expanding upon that further. And so once I graduated, I made the actually truly large leap to Palo Alto, California, where I then started my PhD in electrical engineering at Stanford and have conducted my research within the Congreve lab within the Department of Electrical Engineering. So I wanted to give this background just to suggest that while all my training has been in electrical engineering thus far, I have found time and time again, and especially within my PhD, that in order to make the best possible optoelectronic devices or materials in general, we need to encourage the use of knowledge from across a variety of disciplines, including material science, but as well as chemistry, chemical engineering, and so on and so forth. And so with that, I'll talk about the outline for today's talk, which will be a brief background motivation as to why we should care about perovskite-based light emission. Next, I'll tell the story of how I use manganese dopants to drive the efficiency within perovskite LEDs and uncover this interesting trade-off between the efficiency and stability, followed by several studies towards engineering wide bandgap perovskites to move towards the ultraviolet spectrum. And lastly, I'll conclude with some of the work that I've done towards improving diversity, equity, and inclusion within engineering academia, and hopefully inspire some new pathways after the seminar. So with that, let's get started. Within LEDs, one of the natural applications is solid state lighting. And according to the US Department of Energy, on our current path, we are projected to save 62 quads of energy by 2035, in which one quad is approximately 300 billion kilowatt hours. However, if we pursue a slightly more ambitious program, we can save an additional 16 quads of energy through 2035. And so in total, this cumulative 78 quads of avoided energy by using LED-enabled solid-state lighting, we can avoid around $900 billion in total energy costs. And so this really highlights the importance of innovating at the materials level and the device level to enable next generation solid-state lighting. So the other natural consequence of using LEDs is to use them in next generation displays. And so as we can see here in an iPhone, or more specifically the iPhone 14, uses an OLED screen, which is an organic LED. And so we might see some materials such as ERPI, which will be used as the emissive layer within this device. Next, looking at quantum dot LED technologies, we can see the Samsung Smart TV might use materials such as the cadmium selenide core zinc sulfide shell structure as shown here. And so these displays, at least to me, already look very nice. And so what is there next for us to do, and what kind of materials we want to consider? And so moving from here, we can consider moving towards REC 2020, which is a standard for ultra high definition displays, and focusing on red light emitting devices. And again, focusing on organic materials, cadmium and cadmium-free quantum dots, perovskite nanoparticles, and polycrystalline perovskites. We can see that within this chart, we want to be near the bottom right, in which we will have a lower full width half max, thus having pure color purity within the emitting device, as well as good agreement with this REC 2020 standard. And so for the red device, we can see that the perovskite nanomaterials have both good agreement and pure color purity emission, and that this holds for both green and blue devices as well in general. And so it's not enough just to have great optoelectronic performance. We must also consider having this performance at lower cost. And so comparing the production time and the materials costs across organic and quantum dot and perovskite materials, it is very clear that perovskite materials have great potential from a financial perspective to create next generation displays. And lastly, just looking at the overall agreement with REC 2020, we can see that the perovskites are essentially at 100% agreement. And from the CIE chart, we can span the visible spectrum for ultra high definition displays by using perovskite-based devices. And so the next natural question is to why these materials are particularly attractive and what makes them very, very high definition for these particular applications. And so we can look at lead halide perovskites in general. So first, showing the 3D structure of a lead halide perovskite, they're governed by an ABX3 formula, and where A can be an organic or inorganic cation, B is lead, and X is a halide anion. On the picture on the right, we can see that these materials are solution processable, implying that they are very inexpensive to produce, as well as we can sweep across the visible spectrum with fairly low full width half maximum between 12 and 42 nanometers. And so putting these material properties together, we can say that this material class system is an outstanding candidate for next generation light emission because of their inherent materials properties. And so now moving from here, and to give some background, I'll highlight one of the works from my group before I joined, and specifically in 2019, where they looked at exchanging up to 30% of the lead within the perovskite itself with manganese dopants. And as we can see from this picture here, across green, red, and sky blue devices, we can improve the brightness and film uniformity via this manganese doping. So now focusing on the green light emitting devices, we first define this external quantum efficiency, which is the ratio of the number of photons emitted from the device to the number of carriers injected into the device itself. And we see that we could achieve a maximum 3.2% EQE with increasing manganese doping. Next, for the operational stability of the device, we see that without any manganese doping, this device was less than 1 minute stable, but upon introduction of 30% manganese doping, we can see a half-life time of 23 minutes. And so in general from the study, we learned that by doping these hybrid organic, inorganic lead halide perovskites with these manganese ions, we can improve the brightness, efficiency, and stability of the LED itself. And so while this was an outstanding first step, there is still some more work to be done, and specifically trying to reduce the surface defect states within this thin film. And so with that, there was a new additive class system that has started to emerge known as phosphine oxide additives, in which essentially the phosphine oxide moiety will coordinate with the lead site, which should in turn reduce the surface defect states and thus enhance radiative recombination pathways within the film itself. And lastly, within perovskite PD, we can suppress electron recombination. And so this additive class has a lot of applications within perovskite optoelectronics themselves. And so now looking to how we can follow up on the initial manganese doped work, I then looked at including TFPPO, or trifluorofluorophenylphosphine oxide, within manganese dope thin films. And I focus on concentrations of 0, 5, 10, and 20 milligrams of TFPPO per milliliter of chloroform antisolvent. And we can see here from the PLQY, which is defined as the number of photons emitted to the number of photons absorbed from the thin film, that we can increase this metric to approximately 67%, which is much higher than the approximately 25% value reported back in 2019. Additionally, we can see the stoichiometry of the perovskite that we're working with here, and under UV light, we can see that the films do increase in brightness upon extra towards higher concentrations of TFPPO concentration. Next, looking at the AFM images, we can see that as we move towards higher TFPPO concentration, we can see a change in the morphology of the thin films. And so with this, and encouraged by the higher brightness in these devices, or these films, we then looked at incorporating them into an LED configuration. And so here we're showing the device stack, as well as the energetic band alignment. And there are a few innovations I would like to highlight here that were not included in the 2019 device. So the first one being including this 1.5 nanometer ultra-thin lithium fluoride underlayer, which serves to reduce the exciton quenching that would occur between the PDOT-PSS PFI whole transport layer and the perovskite layer itself, as well as exchanging, and as well the lithium fluoride can increase the wettability of the perovskite, thus enabling more uniform and conformal films. Next, we exchange the electron transport layer of TPBI with 3TPYMB to facilitate the injection of electrons from the lithium fluoride aluminum electrodes into the perovskite conduction band minima as shown here. And so across the TFPPO concentration, we can see that there is no apparent red or blue shift with increasing TFPPO concentration, and see very clear, approximately 520 nanometer centered green light, pure, very bright manganese doped LEDs, and it can also be shown in the inset here. So now focusing on the device performance, we first turn our focus to the champion efficiency devices, in which we can see that they achieve very good turn on voltage at approximately 2.5 to 3 volts, as well as achieving high luminance values of approximately 100,000 candela per meter squared. Now, while not shown here, our champion brightness devices did achieve luminances as high as 128,000 candela per meter squared, which are among the highest reported in the perovskite LED literature. So now looking at the characteristics of the external quantum efficiency versus the voltage, we can see that with TFPPO concentration, we can monotonically increase the peak external quantum efficiency to now a new record of 14.0%. And in order to make sure that this is not a one-off case, we looked at conducting device statistics across approximately 120 devices, and see that we do see this approximate 5x improvement in EQE, and thus we can definitively say that TFPPO definitely improves the efficiency of these green manganese doped perovskite LEDs. And so while we're off to a great start, we also need to consider that if we want to truly evaluate the performance of an emerging light emitting technology, we need to consider both the stability as well as the efficiency in order to drive the commercial viability. And so that's what we'll focus our efforts next. So within the operational stability of these devices, we look at the champion stability luminance evolution curves, and we can see that we can extract several half lifetimes from these curves. So the first one is the T50 time, which is just defined as the time that it takes for the device to reach half of its initial luminance, which for the violet curve is denoted with this violet circle annotated here. And however, since some of these devices experience what is called luminance overshoot, that is, they reach a higher luminance than their initial luminance at time equals 0, we also define an adjusted T50 prime time, which is the time that it takes for the device to reach half of its maximum luminance, adjusted for the time that it actually reaches its maximum luminance. So for this violet curve, that's annotated up above with this annotation here. And so if we extract the adjusted T50 prime and T50 times for all the champion stability devices, the trend remains the same, and that is that while we're increasing the TFPPO concentration, the stability does go down quite severely. And again, to make sure that this is not a one-off effect, we conducted several device statistics across many devices and see that, in fact, the stability does seem to be impaired with higher TFPPO concentration. So now plotting the peak efficiency of the champion efficiency devices and the stability of the champion stability devices, we can see this efficiency stability trade-off start to emerge in these green manganese doped perovskite LEDs. And while unfortunately the TFPPO impairs its stability. It can improve the efficiency, but again, it is at the cost of this dramatic impairment of the stability. So seeing this perplexing trade-off, we then sought to understand it with repeated electrical scanning measurements, as well as time-resolved photoluminescence. So starting with the repeated electrical scans, I'll briefly walk through this experimental setup. So over here, we're focusing on just the 0 mg per mil TFPPO device, in which we take a fresh electrical scan, which is just defined as a current voltage luminance scan at time equals 0. We then stress it for 2 minutes and take a following scan, stress it for 4 minutes and take a following scan, and do this until we have approximately 30 minutes of cumulative electrical operation. And to see this a little bit more in the diagram, we can see that this is how the timing of the scanning and the stressing looks like. And so now looking at all 4 TFPPO concentrations together, we can consider various optoelectronic parameters and their evolution with time and electrical operation. So the first one we might want to consider is the turn-on voltage, which we'll define as the voltage of the device when it reaches a luminance of 1 candela per meter squared, which can be shown as the y-intercept here. So if we look at the TFPPO devices, we can see that in general, the devices that have TFPPO have a larger increase in the turn-on voltage as compared to the device that doesn't have TFPPO. And this implies that there's a greater barrier to the injected charges within the LED device towards the emissive perovskite. Next, we look at the operational luminance, that is the luminance at 10 milliamps per centimeter squared injected into the device, and see that while the TFPPO, the device without any TFPPO, might start at a lower luminance, it does sustain its luminance for much longer, and actually after 30 minutes is the more efficient device as compared to the 5 and 10 milligram per mil TFPPO device. And I would argue that if we extended this even further, this device would potentially be more efficient than the 20 mg per mil device. Finally, looking at the maximum luminance evolution of these devices, we can see again, while the lower TFPPO devices might start off with a lower maximum luminance, they are more robust with cumulative electrical operation, and thus may have more robust stability for high brightness applications such as laser diodes. And so putting the turn-on voltage, operational luminance, and maximum luminance together, we can say that while this TFPPO treatment did initially enhance the device operation, unfortunately, these parameters are not robust with operation as the device is degraded with higher TFPPO concentration. And so lastly, focusing on time-resolved photoluminescence, the experimental setup here is that we take a fresh device, measure its time-resolved photoluminescence decay, followed by an hour at 10 milliamps per centimeter squared electrical degradation, followed by another time-resolved photoluminescence decay. And we can see that all 8 of these curves can be modeled by this bi-exponential decay model shown here. And we can also define an average lifetime, which is a weighted average of the tau1 and tau2 lifetimes, where tau1 is a trap-assisted non-radiated recombination related lifetime, and tau2 is a longer emissive radiated recombination related lifetime. So annotating these tau averages on the charts here, we can see that in general, with higher TFPPO concentration, we see a more significant reduction in the tau average after the operation of the device. And this is largely due to the reduction in both the contribution of the tau2 lifetime, that is B over A plus B, as well as the tau2 longer lifetime itself. And so in order to support these conclusions as well, we also looked at measuring the photoluminescence quantum yield of these devices both before and after degradation. And we can see a clear monotonic decrease with TFPPO concentration, suggesting that its emissive efficiency does go down with higher TFPPO concentration. And so we were able to understand this trade-off between efficiency and stability. I should also mention that within the time-resolved photoluminescence, we saw that the devices that were treated with TFPPO, there is an increase in the tau1 contribution related lifetime, which suggests that a lot of the degradation is happening actually at the perovskite grain boundaries, which makes sense based on the previous report of TFPPO treated devices that says that TFPPO largely serves to passivate those grain boundaries. And so in general, we saw that while TFPPO can increase the EQV by nearly 5-fold, it also unfortunately impairs its stability by nearly 15. And so moving forward, if we were to use this B-site dope perovskite LED platform moving forward, we want to consider how we can keep the energy efficiency boosting properties from this additive class while mitigating the stability degradation mechanisms. And so now I'll move towards the ultraviolet spectrum and specifically how we engineer wide bandgap perovskites in general. And so to motivate this, I think within the beginning of the talk, I've suggested why perovskite LEDs and LEDs in general are important for lighting and display applications. And while we can't see this higher energy light to the human eye, there are very important applications for our society that we need to consider and would benefit from revolutionizing devices within this regime. So the first two that I really want to highlight is water purification and sterilization. So if we engineer devices within this application space, we can improve human health, and this has been very clearly shown how important it was given the recent pandemic. Additionally, there are applications in stereolithography or 3D printing, as well as nanofabrication and sensing that we can unlock using UV light emitting devices. And so previously, it seems that the perovskites, at least in the 3D configuration, are really limited to the visible spectrum. And so how are we going to move into this new high energy regime? So we can learn from the past and essentially look at these 3.5 devices first. And for example, I have here an aluminum gallium nitride 3.5 LED. And what we want to focus on is this aluminum gallium nitride quantum well emissive layer. So these quantum wells use a particle in a box like structure to confine the carriers to reach higher energy light emission. And it turns out we can play a very similar trick with perovskite nanomaterials. So we can use lead bromide octahedra and confine them using this organic phenethylammonium layer to create the exact same quantum well structure and thus emit higher energy light. And so that's what we'll focus our efforts next, focusing on phenethylammonium lead bromide emissive perovskites. So first, we looked at dissolving these perovskite precursors in DMF or DMF water, and the reason for that will become clear very soon. We then used a two-step annealing procedure in which we annealed in DMF vapor to increase the formation of nanoplatelets, followed by a temperature anneal to remove any residual solvents from the process techniques that we've used here. Now, from the AFM images, we compare the films both with water and without water, and focusing first at without water, we can see that this film has fairly large pinholes, which will induce high leakage current, and therefore there will be a lot of current flowing into the LED that will not promote violet light emission in general. However, once we include the water additives, we're able to suppress a lot of the pinholes and create a more conformal film. And so the question now becomes, can we get the same or similar amount of light emission from this device and hopefully at a much lower cost of injected carriers? And so again, encouraged by these results, we then focus on implementing them into a device. So here we have a typical LED structure using PDOT-PSS and PPPI as the transport layers and ITO lithium fluoride aluminum as the electrodes. And we can see that both with the water and without the water additive, we can produce 408 nanometer light emission with a full width half max at 10 nanometers, making this a very pure violet LED. In the inset, we can see where the 8 pixels lie within the substrate, as well as a violet LED under electrical operation. So now focusing on the current voltage radiance characteristics, and first focusing on the current voltage characteristic, we can see that comparing the with water, which is the purple trace, to the without water, which is the red trace, we see much less current at holding voltage constant, which again is thanks to the suppression of the pinholes within the films that we created, and thus we see less leakage current, which is why the red trace has a higher current for across all the voltage that we swept within our measurement. Next, looking at the amount of violet photons that are emitted from the device, we can see that they are fairly comparable between the with water and without water. And even though that the with water device does have the light emission come out at higher voltages, because the current is lower for all the voltage regimes, we should see an increase in the efficiency because we're getting a similar amount of photons at a dramatically reduced cost of injected carriers. And that's exactly what we see here. And with water, we're able to create a violet LED device emitting with an efficiency of 0.41% as compared to the control without water device of 0.08%. And across device statistics, you can see that this is not a one-off phenomenon, and that truly these water additives are enabling bright and efficient 408 nanometer violet emission. So now focusing on the operational stability of these devices, we can see a approximate 2x improvement with water as compared to without water. And we can also see that these devices are spectrally stable, that is maintaining their 408 nanometer violet emission across time. And so I don't want to kid anyone here that, a half lifetime of 0.3 seconds is not really commercially viable, but it does suggest that if we're going to use this material class system further, we really do need to improve the stability of these devices in order to implement them into exciting new technologies. And so moving on from this work, we were very, very close to achieving ultraviolet electroluminescence. And in fact, showing the same phenethylamonium lead bromide film, we achieved a peak photoluminescence at 406 nanometers. And so there is one more trick that we can play to hopefully achieve ultraviolet electroluminescence. And that is, what if we exchange 25% of the bromide within this perovskite with chloride, and thus achieving a phenethylamonium lead chloride 1 bromide 3 mixture? We're able to blue shift the photoluminescence by 13 nanometers and achieve a new peak at 393 nanometers. And thus, we have a greater chance of achieving ultraviolet electroluminescence. So now we focus on making the devices, and we employed the same device architecture that we did previously. However, we don't see any sort of sharp emission, except we see this broad electroluminescence curve with some interesting artifacts around 500 nanometers and some broad emission around 400 nanometers. And so we hypothesized that it seems at this band gap regime for the perovskite thin film that we are likely not confining all of the charge carriers within just the perovskite film itself. It's likely that we are also getting electroluminescence from the TBBI layer. In order to see that, we also made devices that didn't have any perovskite at all and just used TBBI's electroluminescence layer. And we can see that those artifacts around 500 nanometers that are somewhat appearing within this electroluminescence spectrum show up, as well as the broad emission near 400 nanometers. And so in order to circumvent this issue, we then looked at employing TMP-YPB, which is another electron transport layer, to really confine all the electrons and holes within the chloride 1 bromide 3 perovskite. And once we did that, we're able to see sharp emission at 399 nanometers, which is the first UV emitting lead halide perovskite demonstration to date. And so now looking at the performance of this device, we have a terminal voltage at approximately 5 volts, achieving a maximum radius of approximately 33 milliwatt per square radian meter squared. We achieve an external column efficiency of 0.16%, and we see stability lifetimes on par with the violet LED and good spectral stability as the device is operated. And so these 2D metallic perovskites do unlock new pathways towards UV light emission in general. And so you might wonder that the next slide will likely be, okay, then we replace 50% of the bromide with chloride. But we start to encounter severe solubility issues with the perovskite precursor and can't create a conformal film at that point, and thus suffer both at the film and device level. And so new materials need to be considered if we are to move forward. And so recently, we have seen that lanthanide double perovskite nanocrystals using rare earth elements and showcase light emission from the deep UVC spectrum all the way to the near IR. And specifically, I want to focus on the cerium lanthanide double perovskites and show that it has a doublet emission at UVA, or 370 nanometers, and violet, 410 nanometers, largely due to the D to F electronic transition shown here. And so the question here is, could we employ these rare earth elements in a perovskite LED configuration to enable new UV emitting devices? And so again, these materials do also have some solubility issues, but they have the potential to be deposited with a new technique known as thermal evaporation. And so I'll briefly explain how thermal evaporation for perovskite LEDs works. In general, we load the perovskite precursors into these crucibles. Under vacuum, we vaporize them and have the ions and molecules react within the chamber, and then deposit a solvent-free perovskite active layer on the substrate or target surface up above. Now, from this technique, several advantages might be apparent to you, which are that we can increase the reproducibility of the devices from using this technique. We have the potential to use larger device area, and this technique is currently industry compatible because this is the technique that is used for organic LED fabrication. And so why have we focused so much within the perovskite LED community on spin-coated techniques? And that's largely because the efficiency is quite unmatched with any other technique due to the various solvent engineering or additive engineering techniques that we can use within solution process techniques. However, if we're going to move towards a true commercially viable technology, given the advantages in all the other various areas, I do believe that thermal evaporation is going to increase the commercial viability of these LEDs in general. And so now focusing on cesium europium bromide LEDs, by evaporating cesium bromide and europium bromide precursors, this study found that they can create 448 nanometer blue emitting films with a PLQI of approximately 70%. So again, thermally evaporated and purely lead-free. Encouraged by their films, the authors looked at employing a device architecture in which they use an insulator perovskite insulator structure, or an IPI, because the cesium europium bromide has leakage, and because it's thermally evaporated, we can get away with using these ultra thin layers, and thus can suppress leakage current that would occur because of the pinholes within this film. And so by tuning the thicknesses of both the bottom and top lithium fluoride layer, they're able to achieve various current voltage luminance characteristics and eventually landing on a maximum EQE of 6.5%. So inspired by both the lanthanide double perovskite nanocrystals as well as this work, I then sought to evaporate cesium chloride and cerium chloride together, and first looking at the ratio of the amount of material that I would evaporate, both the cesium chloride and the cerium chloride, as well as the individual rates at which they would be evaporated. And eventually found that by evaporating them at a 1-to-1 ratio at 1 angstrom per second, we can achieve very clear 367 nanometer photoluminescence emission with the 400 nanometer shoulder, thus dramatically moving into the UV spectrum as compared to the 2D lead halide perovskites. And so lastly, within the cesium europium bromide work, they also showed the effect of in situ annealing, that is holding the backplate of the samples within the perovskite evaporator, and both based on the photoluminescence and XRD, we can achieve, or they were able to achieve, a more pure blue emission from moving from room temperature to 200 degrees Celsius, as well as from the XRD, they're able to improve the reaction between cesium bromide and europium bromide precursors to create more crystalline cesium europium bromide films. And so we have a very similar capability within our lab as well, in which initially this curve that I just previously showed was deposited at an in situ annealing of 25 degrees Celsius. And then moving at 100 degrees Celsius, we can see that we start to affect the shoulder of this curve. And then because at this time, this was the highest in situ annealing that we could reach, and not quite compared to the 200 degrees Celsius from the cesium europium bromide work, we looked at evaporating films at holding an in situ annealing of 100 degrees Celsius, and then looking at the effects of post-processing annealing. That is just annealing it on a hot plate in the glove box after depositing within the perovskite evaporator. And we can see that there's not a substantial change in the photoluminescence spectrum. However, there is substantial punching that occurs. And so while we have this knob of in situ annealing to affect the 400 nanometer shoulder, the post-deposition annealing seems to just quench the PL intensity. And so at this time, we're working towards further improving this film and hopefully incorporating it into a 366 or 367 nanometer UV perovskite LED that is fully thermally evaporated and lead-free to really encourage the commercial viability of these deep UV emitting technologies. And so that is the conclusion of the research part of the seminar. I will now transition to some of the work that I've done with the Stanford Engineering Research Introductions Organization, which is an organization that I'm the principal founder and president of, and I've very happily supported all of these underrepresented students for the past few years. And so increasing diversity, equity, and inclusion within engineering academia is a very complicated problem, and I want to reduce the scope and show you exactly what it is that Serio has worked on in these past several years. So focusing on the transition from undergraduate to graduate school for underrepresented minorities, we can see that for Black and Hispanic students, it seems that this pipeline is quite leaky. And especially if they want to transition to the higher levels of engineering academia, there needs to be more support and systems in place in order to encourage these very talented and deserving students to enter engineering academia in general. And so within my experience leading the Stanford Engineering Research Introductions Organization, we found several tools to success, as we call, that have encouraged these students to pursue academia further. The first one being personalized graduate student mentorship. At this time, I lead 150 Stanford graduate students towards mentoring 150 underrepresented students across the United States. We really encourage our undergrads to get into the habit of getting into research opportunities very early on in their undergraduate career, to both inform what kind of science they would like to work on, and as well as improving their viability for a future graduate engineering degree. And we also encourage them to connect with faculty members to learn more about engineering academia and thus increase their sense of belonging in general. And so a little bit more specifically, we want to hit on these three main goals, which is we want to increase the knowledge of unspoken expectations or hidden curriculum within engineering academia. We want to inspire these talented and deserving students to pursue graduate school after their undergraduate education. And once they become graduate students, we want to improve their sense of belonging and hopefully retain them and see them usher into the outstanding scientists that they'll become. And so within the context of a conference-style program, specifically the series program, we look to do this through seminars and workshops, lab tours, faculty presentations, and graduate student panels. So now, focusing on the anonymous survey that's conducted at the end of the program, we can see that the evolution of how these students feel about graduate school. So first, we ask them, how did they consider graduate school as a possibility after graduating with their undergraduate degree? And before attending our program, students had a very neutral response. But after attending the program, they seemed very excited and willing to consider graduate school as a real possibility. Next, after our program, we also asked if they felt comfortable or confident in their ability to navigate what can be a complicated graduate school admission process, and see that before attending the program, they feel very unconfident, but afterwards they feel very confident that they could apply for graduate engineering degrees. And lastly, after completing the program, we asked if they feel that the information that they learned would be crucial if they were to apply for a graduate degree and also be successful as a graduate student, and see that the students strongly agree, as well as very intentionally having the conference-style program be housed and have participants that are underrepresented at the graduate student and faculty level. They feel more comfortable at attending a school like Stanford and other peer institutions for their graduate education. And so the take-home message here is that if we demystify the graduate school experience across the board, we increase the likelihood of these talented, underrepresented students to really pursue a graduate engineering degree, and therefore truly improve the diversification, equity, and inclusion within engineering academia in general. And so to end off on this section, I'll just briefly highlight some of the students that all of these students here actually started research when they were freshmen. And so that you can see a few students here conducting some experiments and all the way to presenting their research, even as far as presenting at a recent APS meeting, which is really quite outstanding as an undergraduate student. And so it's really exciting to see that this is the future. And I hope that some of you will reach out or consider reading more in the paper as how you can incorporate some of the methods that we've been successful to really support these underrepresented students. So for the acknowledgements, I just want to acknowledge a few students that I've really gotten to work with and know. So my colleagues Manchen and Junri have been instrumental to developing the ultraviolet work and are very good teammates of mine, and I'm very happy that I've been able to work with them for so long. Next, I've had the great pleasure of working with two very outstanding undergraduate research assistants that also make up us four plus me, make up the LED team within our lab. And I'm really excited to announce that Natalia Marietta will be staying at Stanford EE for a PhD and supported by 3 very prestigious fellowships. And while I'm sad to see him go, I'm really happy for his next steps, and that Will be attending MIT Electrical and Computer Science, the PhD program, as an NSF fellow. Next, I was happy to help mentor Gabriela Bertrand, who is a current engineering undergraduate, one summer in our lab towards developing high PLQY thin films. And lastly, during the pandemic, I had a really nice opportunity to mentor high school students and challenge them to learn as much as they could about semiconductor devices and quantum mechanics in general, and be able to evaluate the commercial viability of perovskite LEDs. And they were actually able to publish their paper in a journal for high schoolers. And so all three of these students are outstanding engineering undergraduates. Jasmine Guzman, I still meet with all the time on campus, and she's a current engineering undergraduate here at Stanford. Leica Traoré is an engineering undergraduate at Princeton, also conducting some research opportunities. And Ryan Schwake is also an engineering undergrad at Johns Hopkins, and we share a passion for music, where he is a very, very talented pianist. So with that, I'd like to thank you all for your attention, acknowledge my group back at Stanford, as well as the organization that I've led these past few years, as well as acknowledge my funding sources, and I'd be happy to take any questions at this time. Thank you so much.
Okay, thank you very much, Sebastian. It was an excellent talk. And so the way the Q&A will work, anyone can chime in at anytime with questions. And why don't I start off? Because I have a couple about the research and then also this, the serial program.
Sure.
So one, maybe a couple. One, when you look at the roles of the grad student mentors and then faculty in your program, and then the outcomes that you showed in the surveys, is there any, like, are there any differences in sort of effectiveness or some complementary kind of roles for the faculty and grad students in helping underrepresented undergrads kind of get more comfortable with and excited about applying to grad school?
Yeah, there are definitely roles that both graduate students and faculty share. The main one being that both of those populations are either currently in or have gone through graduate school, and so they can provide their experiences both at different time scales. Um, as well as typically a lot of, in my experience, what I've noticed is a lot of the Stanford graduate students, especially the underrepresented ones, like to pay it forward. And so by having just that identity background with their mentee, the mentee does feel more comfortable at, really explaining some of the hurdles that they've had to encounter within their undergraduate degree, and feels comfortable disclosing some of their worries if they're to pursue an eventual graduate degree in engineering. On the faculty side, one of the key pros of having faculty connections is having the letters of recommendation that are very important for graduate school admissions. And so by encouraging these underrepresented students that typically feel that they are bothering the faculty's time by asking them to meet or to talk about their journey and their career, we actually encourage them to do so because more often than not, a lot of faculty are very interested in the development of their students. And so by doing that, we increase the strength of the letters of recommendation as well as they get additional advice at the faculty level that will then hopefully encourage these students to move from undergraduate to graduate school in general.
All right, thanks.
Yeah.
Okay, so I had a research question too. Sorry, so Sandy, you can go ahead.
Yeah, can you hear me now?
Yeah, I can.
Okay, great. On the research side, so I was interested about the manganese substitution. Presumably that's for the lead. So I'm not active in this field at all, but my understanding is that efforts to substitute tin for lead have been challenging because the tin readily oxidizes to the 4+ oxidation state. And I might have expected similar things for the manganese. So did you evaluate that, or do you have any comments on that?
Yeah, so you're absolutely correct with the tin oxidation. There has been a lot of efforts within perovskite optoelectronic devices to move to tin, both for the toxicity as well as just in general moving away from lead. Within the manganese doped work, I didn't encounter any sort of, I guess, as severe oxidation or stability issues that are typically seen with lead. In fact, it did seem to make the device more stable. I don't have it within the paper, but I do remember when we were conducting some early on studies of looking at characterizing the photoelastic quantum yield of the devices themselves. We first didn't encapsulate those thin films, and we saw that the films that have manganese versus the ones that didn't, the ones with manganese did seem to be stable for much longer in air, even though they were both processed within an inert glove box. And so my suspicion is that we don't see any sort of this oxidation or reduced material stability with manganese doping that is very spot on as to what you said that will be typically seen with the replacement of lead with tin.
And do you have an idea why? I mean, I guess I don't know if manganese oxide is, MnO is more stable than SnO under ambient conditions against oxidation, or is it something specific and unique to the halide perovskite environment that's stabilizing the Mn2+ oxidation state?
Yeah, I mean, it could be within the perovskite lattice itself by the substitution with the lead site that might be increasing the stability of the material itself. I haven't personally looked at it too closely because again, we were more focused on the device implementation itself. But I do know that there's several groups and actually alumni from my group, that's Mahesh Gangshetty at Mississippi State, that has looked at more of the effects of manganese on the material stability, and it seems that it's still somewhat not well understood.
Okay.
But I'd have
Okay.
to again check up with him and see
Sure,
what's going
sure.
on.
Okay, I'll let others jump in with their questions. Yeah.
Yeah, it's a question about stability, but also on mechanism, sort of apart from the chemistry. And that is that, the halide perovskites first kind of arose to wide attention because of the use in solar cells, so photovoltaics. Now, naturally, there's interest in LEDs. Stability has been an issue for a long time. Some of those issues are getting worked out for photovoltaics. So I'm wondering, what the differences are, and is it sort of a matter of degree, or some intrinsically different approach might be needed for LEDs? Obviously, the carrier densities and photon densities are going to be higher. There's going to be some higher carrier energies, I would think, given what you were quoting for injection voltages. So maybe you could speak to again, either the challenge in matter of degree or activating different mechanisms that require new solutions on the material side.
Yeah, absolutely. So I think the first thing that we want to consider, and I didn't explicitly touch on this during the seminar, is that the operation of LEDs is dramatically different from photovoltaics. And the primary one is that when you're operating an LED, say you're operating a green LED, or the green manganese doped LED, will achieve likely its maximum external quantum efficiency at around 3 to 4 volts. So now we are likely going to see most of that voltage dropped across the perovskite itself. And because the perovskite thin film is only on the order of like 100 nanometers, that is a gargantuan, to put it lightly, electric field across that perovskite layer. And because of the low activation energies of the halides in the perovskite itself, we incur the phenomenon which is known as ion migration, in which those ions are then swept to their corresponding electrodes, and thus that degrades the stability of the device further. The other one is that since none of the layers within the perovskite LED are perfect conductors, we will also incur Joule heating while we operate the devices, and thus, again, this increase in device temperature will also have effects on the stability of the material and the device itself. Right. And so there's a lot of work being done to try to circumvent these issues. In particular, I'll highlight the work from Barry Rand at Princeton, in which they've looked at using tiny thermal heat sinks, as well as using substrates such as graphite to increase the thermal conductivity within the device itself. And they have seen an increase in stability within their devices, as well as improving the conductivity of the transport layers, again, to reduce the amount of Joule heating that would occur in those devices. And so that is a viable pathway. And there are consistently there's a lot of work being done to try to circumvent ion migration, such as using new transport layers or other intermediate layers to reduce the amount of halide ions that would then migrate through the device itself. But in general, those are the two main steps that are being pursued in order to improve the viability of the stability of these devices.
Okay. Yeah, it sounds like there's plenty to work on in that area.
Yeah, absolutely.
All right, do we have any further questions? Okay, if not, we'll wrap up the seminar portion of your virtual visit, Sebastian.
Sure.
So again, for the really clear and excellent talk.
Thank you.